Okay, so right now we're going to talk about the modified Atwood machine. This is the lab that we just completed in class. Now, what the lab consisted of. We had our cart that was on a frictionless track, which is going to be represented here by block A. It was connected with a string over a pulley to a hanging mass, which we're designating here as block B, just to kind of simplify our terms here. We started off the lab by, well, first, constructing individual force diagrams for these individual components. If we're doing a force diagram for block A, we had the force of gravity on A by the Earth pulling it down. We had a force normal on A by the track, and then we had a rightward force of tension on A by B, because that's what was really pulling on it to the right. We did not include a force of friction to the left because there was, well, no friction on the track. We would say that the upward and downward forces balance out because there's no change in motion up or down. So our sum of the forces equations here, our sum of the forces horizontally is just going to be that force of tension. And our sum of the forces vertically is the force normal minus the force of gravity, which overall we said was 0. We also drew a force diagram for block B. For block B, we had a force of gravity on B by the Earth pulling it down, and we had that upward force of tension on B by A. Those are the only things that were exerting a force on block B. We didn't have any left or right forces, so the sum of the forces left and right is really inconsequential, but we can say it's 0 newtons. But the sum of the forces up and down, vertically, is going to be that force of tension minus that force of gravity. But overall, we know that block B moves downwards, and it accelerates downwards, so it's not going to be equal to 0. So really, I should readjust the scale to show that my force of gravity is bigger than my force of tension. These were the individual force diagrams that we ended up with for these two individual parts of our Atwood machine. However, when we drew it all together, and we had that system boundary across, well, everything, both block A and block B, that ended up putting that string that connected A and B together. It put that string inside of our system, so we no longer have a force of tension. Instead, we just have a force of gravity that would be equal to those two components combined. That is our force of gravity of our system by the Earth pointing down. And then we just have a force normal on the system by the track pointing up. And that's the same size as the force normal acting on just block A by itself. Because really, nothing else has changed about that push up from the table or the track. It should be the same size. So we're still including all of the forces we have. It's just because the tension from the string is inside the system, it's not going to be represented on this force diagram. So my sum of the forces ultimately just boils down to the sum of the forces vertically, and it's going to be equal to the force normal minus the force of gravity of the system. However, we also do know for a fact exactly how much larger that force of gravity is than the force normal, even before we assign any quantities to it. It is going to be equal to the amount of gravitational force acting just on that hanging mass, block B, by the Earth. So that's what our sum of the forces vertically is going to be. The sum of the forces horizontally, nothing left and right, so it's just 0. So these are our three force diagrams. We're going to be focusing primarily on the one that's represented here in black, which is going to be the one for the system itself. Because when we were looking at the acceleration of each of these individual parts, we were really looking at the acceleration of the system. By the time we ended up graphing it and determining a general equation, we ended up with what was Newton's second law of motion, which says the sum of the forces is equal to the mass times the acceleration. Once again, we were looking at the mass of the system as a whole when we were looking at that sum of the forces equation. We also know, based on our force diagram, that the sum of the forces of our system, at least vertically, was going to be equal to the force of gravity on block B by the Earth. So if we set these two equations equal to each other, what we end up with is the mass of our system times the acceleration of our system is equal to the force of gravity on block B, the hanging mass, by the Earth. And rearranging this allows us to determine the acceleration. Our acceleration is equal to the force of gravity on block B by the Earth divided by the system mass. Now we can actually quantify the force of gravity on block B by the Earth, and what that would look like is going to be the mass of block B times the gravitational constant. On Earth, that's 9.8 newtons of force for every kilogram of mass. And we also know what the actual system mass can be calculated as. It's the mass of block A plus the mass of block B. This is ultimately how we can determine the acceleration of the entire system. This is the acceleration of block B by itself. This is also the acceleration of block A by itself. But because these two parts of the Atwood machine go in different directions, that might just affect which coordinate system we apply the acceleration to. But once we know this value right here, we can then use that acceleration and the second law of motion to quantify every single force that's acting on block B by itself. We can do the same thing with every single force that's acting on block A by itself. But in order to get to that, with this setup of our Atwood machine, we needed to make sure that we were first analyzing the system itself and relating that back to our force diagram for the system.